This takes us to the last of the 5 algorithms that I am presenting here as quote-unquote standard sorting algorithms. So this last one is called Quicksort, and it too, like Mergesort, requires recursive thinking, or at least it's a lot easier if you think recursively and implement it recursively. Mergesort and Quicksort are in a camp of several interesting algorithms that all sort, at least on average, they sort in time capital theta n log n. I'm not exactly sure when Quicksort was introduced, but it seems to me that I'm on safe ground asserting that Quicksort has tended to be the most popular ever since its introduction of these so-called capital theta n log n sorting algorithms. And that's because it seems to be a little faster. And of course, all this depends on implementation issues and the number of subtleties. But anyway, that's my assertion, and I'm not going to try to prove it. But I think generally the constant capital C, the factor C, is smaller for Quicksort than for Mergesort. I've done some tests, and I've compared Quicksort with Mergesort, and also a popular predecessor of Quicksort's was a sorting algorithm by a man named Donald Shell, and the so-called Shell sort, also capital theta n log n, was quite popular in its day. But my impression is a Quicksort tends to nudge out all of these. There are several versions of Quicksort. There's a lot of subtle variations, particularly in the choice of what's called the pivot. We'll get to that in a minute. The pivot is simply a particular entry in the array, but usually it's a rather arbitrary entry in the array. Anyway, I've chosen to introduce the version of Quicksort that is spelled out in Chapter 7 of the book by Corman, Lieserson, Rivest, and Stein. And I'm going to present C++ code that's equivalent to the pseudocode that they give. And I've chosen this because the code is a little more direct than anything else I've seen, and therefore it's a little easier to implement and analyze. All right, so here's the basic strategy for using Quicksort to sort a portion of an array. Okay, first you have to select some entry in that subarray to play the role of a pivot. And as I said, we're going to take the entry that's furthest to the right in the subarray and let that play the role of the pivot. Then it's simply a matter of scanning the subarray from left to right, and anytime we encounter an element that's less than or equal to the pivot, we swap it so as to put it towards the left side of the subarray. And we do this in such a manner that by the time we're done scanning the entire subarray, it's guaranteed that everything that is less than or equal to the pivot comes before everything that's greater than the pivot. And then the pivot itself is swapped into position and winds up exactly where it belongs in the subarray. And then everything before the pivot is less than or equal to it, and everything after the pivot is greater than the pivot. So then it becomes a very simple matter of calling quicksort recursively two times. Call it to sort the subarray consisting of everything to the left of the pivot, and call it recursively to sort everything to the right of the pivot. And once those two recursive calls are completed, then it's guaranteed that the entire subarray we were looking at is now sorted. Okay, so here it goes. This is the code, and I think it will quickly capture what I just said. Okay? The header is familiar, similar to what we did with Mergesort, except we don't require the auxiliary array. There's no auxiliary array Q here, but the rest is the same. Okay, there's the array we want to sort P. We only want to sort from position left to position right, and those two default to 0 and n-1 when they're not specified. Okay? The variable pivot will hold some entry from that array, as we discussed. There are also two integers to be used as indices, I and j. Okay? Similar to Mergesort, the body of this array is wrapped inside the condition if left is less than right. It's only in that case that we want to do any work at all, just like with Mergesort. Okay. First step, take what's in position right of the array and copy it into pivot. Simple. Okay. The variable I is actually being set to 1 less than the left index, and this could be done differently, but this is how it's done here in order to match to line up with the pseudocode in the book. Okay, then comes a for loop for the purpose of scanning from left to right. The index j is used for that purpose. Okay, and then anytime that p bracket j is less than or equal to the pivot, we simply swap p bracket j with p bracket plus plus I. So what does that mean? You may not be really up to speed with the plus plus operator. The fact that it's in front of the I means that I gets incremented prior to using it as an index into the array P. So remember that it started off being 1 less than left. So the very first time it's used here, it'll first increment it from left minus 1 to left. Okay? So the first time it's used here, this will read P bracket left. And we'll be swapping something that we just found that's less than or equal to the pivot into that position, P bracket left. And you can see that I will always be the index for the last thing that we swapped in to the left side of the subarray. Okay, everything up to index I will be guaranteed to be, all of the entries in the subarray up to index I will be guaranteed to be less than or equal to. Okay? By the time this thing is done, as I said, guaranteed that everything between index left and index I is less than or equal to pivot, and everything after that is greater than index pivot. Okay? And then it's necessary to swap the pivot itself, which is still in position right. It's necessary to swap that into the correct position. and that would be obtained by incrementing I one more time, and that would set I exactly equal to the position where the pivot belongs. And so this final swap will put the pivot where it belongs. Everything to the left of it will be less than or equal to it. Everything to the right of it will be greater than or equal to it. So as indicated a couple times now, all that remains to be done is to recursively quicksort from position left to position I minus 1, that is the stuff that's to the left of the pivot, and also quicksort from position I plus 1 to right, that is everything after quicksort. When that's done, the entire segment of the array from left to right will be sorted. We're going to later return to a careful, or at least a more careful, analysis of quicksort and its time complexity after we discuss recurrence relations and something that the book of Corman et al. Refers to as the master theorem. But turns out, and we'll just say so, on average, quicksort sorts with time complexity capital theta n log n, just like Mergesort. Okay? However, things can go wrong with quicksort. In the worst case, quicksort sorts in time capital theta n squared. Okay? And it isn't difficult to imagine the worst case. It's not too hard to see what can go wrong here. Quicksort, as I said, tends to be faster than Mergesort, tends to be a little bit. But it is not so clear how many levels of recursion it will require. Hopefully you got your head around Mergesort and the fact that at each level of recursion, the size of the list that you're involved with gets cut in half. And that makes it pretty straightforward to count the number of levels of recursion and conclude that, well, it's basically base 2 logarithm of n. Base 2 logarithm of n, maybe plus or minus 1, doesn't matter. But with quicksort, we can't say that. The problem is we don't know what the sizes of the two sublists will be. If we're lucky, they'll be nearly equal. We'll take a big list and cut it into two sublists of nearly equal size. But if we're unlucky, we might take a big list and cut it into two sublists, one of which is tiny and the other one is substantial, maybe almost the original one. All right, so here's how quicksort can go very bad. Here's the absolutely worst scenario for quicksort. So you start with an array of length n, and you're very unlucky because quicksort chooses a pivot that happens to be either the greatest or the least element of that array. As a consequence, the pivot will be placed either at the start or the end, and one of the two subarrays that you end up with will have length n minus 1. The other one will be empty. Okay? So you see what can happen. When you now recursively call quicksort on the subarray of length n minus 1, you might once again end up with quicksort choosing a pivot that's either greatest or smallest, and this results in a subarray of length n minus 2, and that process continues. You get a subarray of length n minus 3, and you keep having bad luck at every level of recursion all the way down until you finally get down to a subarray of length 1. Okay? So, you started with a subarray of length n, went to n minus 1, n minus 2, ... until you get down to 1. So basically that's what? N levels of recursion. All right? Rather than the nice base 2 logarithm of n, you're ending up with n as the number of levels of recursion. And that has a profound effect. So here it is. When you tally that all up, you of course get an amount of time that's a constant times n for the top level, plus a constant times n minus 1 for the next level, plus a constant times n minus 2, plus ... all the way down to constant times 1, and that's equal to, if you factor out the constant and rearrange the terms, you get a constant times 1 plus 2 plus 3 plus ... to n, which is, of course, constant times n plus 1 over 2. In other words, capital theta n squared. All right? There you go. The punchline. In the worst case, quicksort has a time complexity, just like bubble sort, selection sort, and insertion sort.